every scientific field has its own vocabulary, and thermodynamics is not different. Clearly defining basic concepts provide a solid foundation for the development of science and helps prevent misunderstanding. In this video series, I will begin with an overview of thermodynamics and then move on to discuss some of the basic, crucial and important concepts. This video will be a series of videos covering the essential, basic and the mathematics of thermodynamics, and this is the first video. My name is Shaunak and you're welcome to watch this video on my channel Physics for Students for the first episode, Thermodynamics, a Beginner's Guide for Undergraduate Engineering Students. First, we would speak of this, thermodynamics and energy. Well, thermodynamics can be defined as the science of energy. But as you see that although everybody has a feeling of what energy is, it is difficult to give a precise definition for energy. It can be viewed on the ability to make some changes. Now, if we go back, as we used to do, to the etymology of the word thermodynamics, it comes from this Greek word thermos, which means heat in Greek, and dynamic, which means force or power, or you can say it is related to the study of motion and forces. So thermos plus dynamics total makes up the thermodynamics. And if I go further and elucidate, it would look like the study of relationship between heat, energy and the forces or motion, and that these results for these interactions. Also, thermodynamics is a branch of science and engineering that deals with the study of energy and the interrelationship between heat and work and various physical properties of matter. Now, this interrelationship between heat and work, this is the core of thermodynamics, and the entire mathematics, the science, the inventions, everything revolves around this. So from here, what we find is an important factor, which is one of the most fundamental laws of nature, is the conservation of energy principle. Now, I hope you know, but it is still a good time to repeat that it simply states that during an interaction, energy can change from one form to another, but the total amount of energy always remains constant. I mean to say, this is the fundamental core of the conservation of energy principle. So energy cannot be created or destroyed. So here is a demonstration that a rock falling off a cliff, for example, picks up a speed, and as a result its potential energy is converted into kinetic energy. As you can see here, the potential energy was 10 units, it goes to 7 units, and the kinetic energy, which was 0, goes into 3 units. So the conservation of energy principle, I would say, also forms the backbone of the diet industry. Now, what do I mean by diet industry? Let me show you a funny picture. I hope you will understand. So a person who is gaining, I would say, greater energy, or he was taking an input food than energy output, will obviously gain weights and store energy in the form of fat. So and a person who has a smaller energy input than output will lose weight. So here is kind of a simple equation. The change in the energy of a body content on other person is equal to the difference between the energy input and the energy output, and that is being balanced. So here is a person, as you can see, the energy input going inside 5 units, the amount of energy stored in 1 unit, and the amount of energy out for 4 units. So the change in the energy actually is basically the content of a body or any other system which equals to the difference between the energy input and the energy output. This brings to the core of what we call the first law of thermodynamics. In simple words, it can be stated is a simple expression of the conservation of the energy principle. And what it asserts is that energy is, I would say, energy is a thermodynamic property. This also brings up to the second law of thermodynamics, which asserts that energy has quality as well as quantity, and actual process occur in the direction of decreasing quality of energy. So this brings us to the two rules of thermodynamics, first and the second. Now let me give you a quick example. For example, this is a coffee cup. So a cup of hot coffee on the table eventually cools, but a cup of cool coffee in the same room never gets hot by itself. So the higher temperature energy of the coffee is degraded, or I would say transformed into a less useful form, a lower temperature, once it is transferred to the surrounding air. Now, although the principles of thermodynamics have an existence since the creation of the universe, yet the thermodynamics did not emerge as a science until the construction of the first successful atmospheric steam engines in England. It started all in England, and I won't go into the history, but just take a quick tour into what is called the atmospheric steam engines and how did it actually fomented the entire industry and the mathematics of thermodynamics. So Thomas Savery invented one of the first, I would say, steam powered devices. This is also known as the miner's friend. In 1698, it was designed to pump water out of mines, and Savery's engine and steam pressure to create a vacuum that drew water up from the mines. Also, as you can see, Thomas Newcomen improved upon Savery's design. As you can see, this is a schematic diagram, by developing the first practical atmospheric steam engine around 1712. Newcomen's engine and a piston, as you can see on the figure, and a cylinder which allowed for far more efficiency and reliable water pumping. So the design laid actually the groundwork for future steam engines advancements and significantly improving the efficiency of pumping water out of mines. So the atmospheric steam engines, a few good quick features. It was one of the earliest steam engines. It uses a piston and a cylinder mechanism where steam is introduced into the cylinder. The steam is then condensed by cooling, creating a vacuum. The atmospheric pressure pushes the piston down to the vacuum created in the cylinder, and this was a kind of a precursor to the more efficient steam engines developed by James Watt. So although the atmospheric steam engine was basically a kind of an initiation of the main diagram of the main output, so these engines were definitely slow and inefficient. They laid the groundwork for the development of the new science, and Savery's engine was primarily used for pumping water, and later it was designed in order to make the, I would say, the first practical use for mining. But apart from, I would say, Thomas Savery and Newcomen, there were few more people who made a significant difference in terms of contribution of thermodynamics. So the first and the second law of thermodynamics, I would say, emerged simultaneously in 1815, primarily out of the works of William Rankine, Rudolf Clausius, and Lord Kelvin, formerly William Thomson, and the term thermodynamics was first used in a publication by Lord Kelvin around 1849, and the first thermodynamics textbook was written in 1859 by William Rankine, a professor at the University of Glasgow. So this actually shows the evolution of the, I would say, atmospheric engine, and how the steam engine and the, I would say, the seed was basically planted. Now, we all know, it is well known that a substance consists of a large number of particles which we know as molecules. Now, the properties of the substance naturally depends on the behavior of these particles. So, for example, the pressure of a gas in a container, as you can see on the figure, is the result of a momentum transfer between the molecules and the walls of the container. Now, obviously, one does not need to know the behavior of the gas particles to determine the pressure of the container. Why? Because we would just attach a kind of a pressure gauge to the container and we would come to know. So we really don't need to go the inside part. Now, why I'm telling you this? Because the macroscopic approach to the study of thermodynamics that does not require knowledge of the behavior of the individual particles happening is called classical thermodynamics. And it provides a direct and easy way to the solution of engineering problem, and a more elaborate approach based on the average behavior of large groups of individual particles is studied through what we call statistical thermodynamics, and the microscopic approach is rather involved and is used in this text and only in the supporting role. So the two areas, the classical and the statistical, clearly lays out that what is used for what. Now, when we talk of what is basically used for what, we are trying to tell what we call is the application areas of thermodynamics. Coming up into the next part of the video, we will just take a quick tour into what are the applications of thermodynamics. Now, in all activities in nature involves some interaction between matter and energy, that is for sure. And it is very hard to imagine an area that does not relate to thermodynamics in some manner. Therefore, developing and understanding a basic principle of thermodynamics has long been an essential part of engineering education. So thermodynamics is commonly encountered in many engineering systems and other aspects of life. And one does not need to give, I would say, go very far as the systems and aspects of it is concerned. The heart, for example, is constantly pumping blood to all parts of the human body. Various energy conversion occurs in trillions of body cells, and the body heat generated is constantly rejected to the environment. So even if we consider the human comfort as closely tied to the rate of metabolic heat rejection, they control the heat transfer in terms of household utensils. Everywhere you will find that the thermodynamics is being used. So really we don't extend our horizon or extend our imagination far beyond that we need to really go out to extreme circumstances to find out thermodynamics. No, we can find out just looking around here. Now, other application of thermodynamics, although there are many, just to summarize, are right here on our lives, or an ordinary household, which I showed you, an exhibition of all those things. Some examples will be the electric or the gas range, the heater, the refrigeration part, the humidifier, the pressure cooker, and whatnot. So all those things, a lot of functionalities actually emerge into terms of thermodynamics. It also takes part in a major role in automotive engines, rockets, jet engines, and conventional nuclear plants. Now, when we talk of application of thermodynamics in every sphere of life, what we are also trying to know is that these measurements, these effects in terms of heating or cooling requires a kind of a measurement. And how do we measure them? We measure them in terms of dimensions and units. So we would quickly look into, because these dimensions are a little bit different from the conventional dimensions. What are the dimensions and units of thermodynamics? We know that any physical quantity, for example, this pencil, can be characterized by dimensions. The magnitudes assigned to the dimensions are what we call units. Some basic dimensions such as mass, length, time, and temperature, capital T, are selected as primary or fundamental dimension, while others such as velocity and energy and volumes are expressed in terms of, I would say, secondary dimension or derived dimensions. Now, based on the traditional scheme introduced in 1967, so there are two methods. One is called the English system, United States customary system, and another is called the SI, or the international system. Now, based on the notational scheme which was introduced in 1967, the degree symbol was officially dropped from the absolute temperature unit, and all unit names were written without capitalization, even if they're derived from proper names, as you can see over here. So this is a kind of a diagram where the meter, mass, kilogram. I know this is very rudimentary, but however, this is how the units actually originated and they are functioning. Now, here is a very basic concept which is called dimensional homogeneity, and this is where we need to come down and reduce the units to one single unit. For example, from the class, I would say class 1, or from our school grades, we know that somehow we cannot add an apple to an orange. So this is, we all know from grade school that apples and oranges cannot add. But we somehow manage to know that by mistake, of course, in engineering, all equations must be dimensionally homogeneous. So here is a nice figure. So salami plus lettuce plus olives plus mayonnaise plus cheese plus pickles would ultimately lead to Thomas' upset of stomach. Although the first part, salami, is one of my favorite food. So this is actually trying to tell that too much of heterogeneous, I would say, dimensions would not help into something. So every term in an equation must be reduced to the same unit. So here is a note of caution that when we are doing an engineering analysis, attempting to add quantities with different units is a red flag. That means it's a problem. It's a mistake. It's an error. So this mismatch indicates a potential error, and you need to check on those areas. So every term and an equation must have what we call as the same unit. Now here is a catch. I've given this kind of an equation over here, and there is a kind of an error in terms of unit. Now if you can find out the error in this particular equation, please let me know in the comment box. I would be happy that you have really watched the video and you can now find out what's the error, and you are basically reducing them to what is called a dimensional homogeneity, where all the equation terms are equal. Now I would like to give you a quick example. Say for example, we find ourselves in a position where we add two different quantities that are different units. We know that is a mistake. So here is a problem, that the oil and the substance etc. is given, and we need to actually find out what we call is the mass. So this could be a kind of a problem. A tank is filled with oil whose density, as you can see, 850 kilogram meter cube. If the volume rho is the tank, V equals to 2m cube. Determine the amount of mass of m in the tank. I know it is too simple, but what is important is that, so this is the volume, this is the density, and so we would assume in this way that oil is an incompressible substance and thus density is constant. Suppose, I would say, suppose we don't know the volume etc. So a sketch of the system, as you can see on the figure, if we forgot the formula that relates to mass and density and volume, however we know that mass has the unit of kilogram, for example, and that is whatever the calculations we do, we should end up with this, the unit of the kilogram, putting the given formation into this perspective. From there we get into this, and it is obvious that we can eliminate the m cube and end up with kilogram by multiplying the two equations, and therefore the formula we should look is this, and from here we get the answer as 1700 kilogram. So we are eliminating this m cube. So this is a nice startup example that how we can eliminate those units which are not required, or we can make them into a homogeneous. But remember that this approach may not work for more complicated formulas. So keep it in mind that a formula that is not dimensionally homogeneous is definitely wrong, but a dimensionally homogeneous formula is not necessarily right. Now I would like to give you another example. For example, you have purchased this, right? So when you buy a box of breakfast cereal, what it tells, the printing might say that net weight is so and so. So as I've shown in this figure. So what does this mean? It technically means that the cereal inside the box weighed 1000 lbf on earth and has a mass of this much, 0.4536 kilogram. Now using Newton's second law, the actual weight of the cereal in the metric system is this, and we can calculate into this. So I mean to say, this is just a quick example that how much we can calculate, and it ultimately results into 4.45 Newton. So these are simple examples in order to demonstrate how things are working, how things are going ahead. And once we have calculated this, now we come to another thing, that all those formulas and things are what is called is a system. And here we have to define few things, what is called a system and control volumes. So a system is defined as a quantity of matter in space chosen for study. So I would take a very simple example. So the mass of a region outside the system is called the surroundings, as depicted in this figure. The real or imaginary surface that separates the system of its surrounding is called the boundary. And here you can see that the real and imaginary part is the boundary, and there are a few features which is very important, that the boundary of a system can be fixed or movable. The boundary is the contact surface shared by both the systems and the surroundings, and mathematically we can say that the boundary has zero thickness, and thus it can neither contain any mass or occupy any volume or space. So this is a example of what we called is a closed system, and I will now define what is the difference between closed and an open system. So here there is two systems. A system may be considered to be closed or open depending on whether a fixed mass or a fixed volume in space is chosen for study. So a closed system, I would say, is a system that also has known as a control mass. So energy is in the form of heat or work can cross the boundary. So consists of a fixed amount of mass and a mass that is. So from here what we get is that if as a special case, if an energy is not allowed to cross the boundary, so we call it as an isolated system. So these are important definitions. As I was telling, the basic idea of this video is to make the definitions and the foundation clear. So closed system, which is known as a control mass, consists of a fixed amount of mass and no mass can cross its boundary. No mass can enter or leave a closed system, and energy in the form of heat or work can cross the boundary, and the volume of a closed system does not have to be fixed. If as a special case even energy is not allowed to cross the boundary, that is called an isolated system. Now considering this kind of a diagram, engineering diagram, where there is a piston and a cylinder device, let us say that we should like to find out what happens to the enclosed gas when it is isolated. So how to find out what happens to the enclosed gas when it is heated? Now let us find out what actually it happens. So since we are focusing our attention onto the gas, it is in our system, the inner surfaces of the piston and the cylinder form the boundary, right? The inner surface of the piston and the cylinder form the boundary, and since no mass is crossing this boundary, it is a closed system. So mass cannot cross a boundary of a closed system, but energy can, and a closed system of a moving boundary. So here is something important to note, that energy may cross the boundary, and part of the boundary, that is the inner surface of the piston in this case, may move. Everything outside the gas, including the piston and the cylinder, is what we consider as the surroundings. So here is a diagram of what is called an open control volume. So an open system or a control volume is often called a property, any property of a selected region in space. It usually encloses the device that involves a mass flow, such as a compressor, you can call as a turbine, a nozzle, or in case of a water heater. And there can be many more examples. Right. So it flows through these devices is best studied by selecting the region within the device of the control volume. Both mass and energy can cross the boundary of a control volume. Now, a large number of engineering problems involving mass flow and out of systems, and therefore are modeled as control volumes. So a water heater, car radiator, turbine, and a compressor. So I mean to say all which involves mass flow should be analyzed as a control system, that is an open system, instead of control mass as closed system in general. So what we can say, if you can take this kind of an arbitrary region, so in general any arbitrary region in space can be selected as a control volume. It can be selected as a control volume. Now the boundaries of a control volume are called control surface, and they can be real or imaginary. Here you can see the boundaries of the control surface. So it can be imaginary or it can be real. So in the case of a nozzle, the inner surface of the nozzle form the real part of the boundary, as you can see in this picture, and the entrance and exit areas form the imaginary part, since there are no physical surfaces. So most control volumes, I would say, have fixed boundaries. Most control volumes have fixed boundaries, and you can see that however the fixed boundaries and thus do not involve any moving boundaries. So here it is a control volume with fixed and moving boundaries. So in all, what we talk of that most control volumes have fixed boundaries and therefore do not involve any moving boundaries, because that is how it is. And like a closed system, a control volume can experience heat and work interactions. So from here we come to a final summation of what we can call is a control volume. So here you can see that a control volume is a specific imaginary region in space that we basically use to analyze. I mean to say it is hypothetical or theoretical. It is essential. It is an essential mathematical tool to help us to study mass and energy behave within a system. Here are some of the important aspects of control volumes. It has got a fixed region. Number two, there is a fluid flow. So a control volume allows mass to flow in and across its boundaries, which is called the control surface, and we use this concept in order to understand what we call the principle of conservation of mass and energy. So the mass energy analysis, etc., are being carried on over here. So this is basically the foundation. So don't think that this is going to be the final video and that's it. This is how it's closed. No, I've just started building up the basics of the thermodynamics. So we will follow with the dimension units and then specific gravity coming up into the next part of the video and various other things. So thank you very much for watching this video. If you have liked this video, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. This is my email ID. You can subscribe to my other channel on general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. So I will be continuing with this thermodynamics part 1, part 2 and so on until all the basic and fundamental concepts are very clear. Thank you very much for watching this video.